wanted to thank you for your understanding. As I said, today I was not going to be able to be in class in person because of jury duty. And I'm recording this lecture for you. So this lecture is going to be the same for both sections. And what I would like to do is to go into my iPad and then continue on the material we had started on Wednesday. So here, first of all, I will need to share screen. Okay, so I will start with a simple and brief review of what we covered on Wednesday. And when I remind you about the solenoid, so what we did a few lectures before today was to look at multiple loops or coils, as we call them, aligning with the appropriate direction of the current, so their magnetic fields constructively superimposed through their loops. And then in that case, we had, and I would like to show here some of these figures that we did. Go here, for example, one of those, you could see that we analyze that particular structure, and then we found for it that the inductance, the total inductance for this structure has this particular form. So this one. Then we extended that to solenoid. And so that I don't go through this, we explain why in the solenoid, the magnetic field primarily, and specifically the magnetic flux density, primarily concentrates in the magnetic core, because the magnetic core, any magnetic core, has a very high permeability, and specifically the relative permeability of the magnetic core is above 100,000 as a number, which primarily makes the magnetic flux density very high within magnetic materials. And from there, we came to the conclusion that when we solve the solenoid problem, then we find two very distinct approximations for the inductance of the solenoid. In this particular case, the solenoid has n number of coils or loops, as we call them, and then it's fed by a current I, as you can see here, which in fact makes the direction of the magnetic field to be along here and this direction. So we solved that particular problem, and then we found two distinct solutions. One, when the number of coils is relatively small. And what does that really mean? That n can take the values of, say, 2, 3, 4, up to 10. And then, so we got this formula. And then we got also another one where n can have very large numbers, can take very large numbers. And then, for example, 50, 60, and so forth, up to 1,000. And in this case, we have a new parameter that comes into the picture, and that is the length of the solenoid, which in fact here, it would be this. It's the length of the magnetic core. And in that particular case, we have a different expression for the inductance. Now, these two expressions are only equal when L equals 2A. So when L becomes 2A, then LM1 and LM2 become the same. However, when that identity does not apply, so when L is different than 2A, then depending on the value of L, and of course, depending on the number of coils you have around the core, then one or the other can be bigger. The two, however, define a range of values. And which one you're using depends, as we said, on the number of coils. Both of these expressions are approximate. If you really want to solve the problem accurately, that you really need to go and solve the differential equations that we have, like Ampere's law, everywhere in the solenoid, and people have done that, and in the notes you will see how the computations are practically leading into a very accurate representation of the magnetic flux density within the magnetic core. And it is, as we have suggested, much higher than the magnetic flux density outside of the coil. So for all practical purposes, when you have a solenoid with a core, we assume that the magnetic flux density only exists in the core and not outside. And that is a very good assumption. Now, we made some assumptions also when we looked at this problem, and then when we calculated, or at least derived, not really accurately, but conceptually, we derived the direction of the magnetic field in the coil. We applied some conditions between the air, which is outside of the coil here, and the magnetic material there. So we applied indirectly conditions at the interface for the magnetic flux density and the magnetic field, which now we are going to specify more clearly. All right, we indirectly applied those conditions, and then we came out with this picture on how the magnetic flux density is excited inside a solenoid that has a magnetic core. But now, as I said, we are going to more specifically speak about boundary conditions for a magnetostatic field. And we are going to separate the cases into two. One where we have a dielectric material, and one where we have a magnetic dielectric air interface, so a dielectric material and air around it, and the other where we have a magnetic air interface. So let's start with the dielectric air interface. Air interface. And that's case one. So we have a dielectric here. and we have a current that flows somewhere. The current can be on the interface, or it can be somewhere inside. And the current obviously is not going to be, it's going to be a current that is flowing in a wire. All right, it's not like any piece of current that can stand by itself. All right, so now let's write the equations that characterize this field. And what we have two important equations. One, which tells us that the curl of H is equal to J, and the other that tells us that well, there is one more that we have not seen before, but I will introduce that the divergence of B equals 0. And that is because we don't have magnetic charges. And then the other, so the first one is Ampere's law, the second one is the divergence of B. And then we have the Biot-Savart equation that says that B is mu over 4 pi, and then is let's say J, the current. In fact, here is a vector. Divided by magnitude of R to the cube, the third power. And this one specifically gives us the magnetic field everywhere in a distance R away from the current. So if we have here a differential current like this, all right, and that is D sub J, which is going to be JDL, and that's DL, then that differential current creates a dB, which is given by that. And then at any point away from this differential current, we are exciting a differential magnetic flux density that is given by that. And that's the Biot-Savart law. All right. What we see here is everywhere the magnetic flux density B, whether it is the differential magnetic flux density coming from a differential current or like a total magnetic flux density, it only depends on the value of mu. So it changes, for example, drastically from one medium to another if the medium, the media, or one of them is a magnetic, and therefore mu changes substantially, all right? As we remember, only magnetic materials have a mu which is different from mu naught. And dielectric materials have a dielectric permittivity which is different than epsilon naught. So in an air dielectric interface, here, epsilon is equal to epsilon R epsilon naught, and mu is equal to mu naught. That's what happens in dielectrics. And here, in free space, we have epsilon naught and mu naught. So what we observe here is that in terms of mu, air and dielectric behave the same way. And therefore, for a magnetostatic field, the presence of a dielectric material is not visible. So the magnetostatic field practically is blind to dielectrics, which is very interesting. However, that is not true with magnetics. So now if we go to a magnetic air interface, and now let me take this here and copy it, put it here. And I will change a few things. So first of all, I will remove this. I will use a different color to indicate this material. And now this material is magnetic. So here we have that mu is equal to mu sub r epsilon, mu sub naught, and epsilon is equal to epsilon naught. Okay. Now, if we take these equations here, copy them, and place them, what we have, in fact, I will write it here, is that the curl of B, which is Ampere's law, I just multiply by a mu, and then gives me curl of B is equal to mu J, and the divergence of B is 0, primarily because we don't have charges. And then down here we have Biot-Savart law. So now, as you can see, depending on where the R is, if for example I have another R, another point rather, which is here in free space. So dB here, dB prime, is gonna be given by the following expression: mu naught 4 pi dj cross r, magnitude of r to the cube to the third power. So you see that even for the same distance from the source, same as vector, all right? So both in magnitude and direction. I mean, direction could be, however, in air. The two values of the magnetic field are different. Why is that? Because one is in air and the other is in the magnetic. Therefore, in the air magnetic interface, we have important boundary conditions which we do not see for the magnetostatic field in an air dielectric interface. In the air, as we said, the dielectric for a magnetostatic field is like not present. So the magnetostatic field is blind. I mean, it's like, does not exist for a dielectric. So the magnetostatic field does not see it, and it does not matter for it. Okay, so now, however, we are in a magnetic air interface. So I will take the same interface at this moment. Copy. And then I will consider two cases. One, a magnetic air interface without currents in the vicinity, without a current. in the space of interest, in the region of interest. Which means that I will take this out and we will assume now that the magnetic field has been generated by a source, an electric current, obviously, but an electric current that is far away from our place of interest, our region of interest, where we are looking at values of the magnetic field. So it is not in the vicinity of where we are. Okay, so now let's assume that there is here a magnetic field B, 1, and then I will call this space 1. And then I will call this space 2, which is the magnetic. And then B1 is here, the field in this region, and B2 is the field in the magnetic material. So now I'm going to take here a point, consider a point, say O, observation point, and then I will also take the direction or the vector, which is normal, to the interface at that point. And now the two boundary conditions that are of importance say the following, that N cross B1 minus B2 is 0, and also N dot B1 minus B2 is 0. As a matter of fact, I will assume at this moment, yeah. Now, if we add a current on the interface, J, then this field changes. So let me, in fact, also now remove this condition, all right, which I entered in the beginning. And in this case, I will have that this one is going to be equal to J. And that makes it more general. So if J is there, then the cross product between the direction normal to the interface at that point of interest with the B1 and B2 is equal, the cross product between that vertical vector and the difference between B1 and B2 equals to J. And I will explain now what that means. So only I'm reading this mathematical expression, while the dot product between N and the difference between B1 and B2 equals 0. What does those mean? So the first one, take this here and this here. The first one, let's see what it says. It says that the cross product between B1 and B2, when there is a current, is not continuous. So in other words, I could write here that N cross B1 minus N cross B2 equals J. So what is cross N cross B1? This is a tangential component, of B1 on the interface, and that is a tangential component of B2 on the interface. So the tangential components of the two magnetic fields are not continuous if there is a current in there. All right, if there is a current on the interface, the tangential components of the magnetic field are discontinuous, and that discontinuity is equal to the current that exists at that point in space. Okay, while here, that is one. While here, the other condition says that the N dot B1 is equal to N dot B2, and that says that the normal component of B is continuous through an interface. Air magnetic interface. Here I left out a mu, and right, so we need to remember that. All right. So the tangential component is discontinuous if there is a current. The normal component is continuous no matter whether there is a current or not. And these are what the two important boundary conditions are telling us about an interface. Now, if there is no current at that point on the interface, obviously both tangential components of the magnetic flux density and the normal components of the magnetic flux density are continuous. Now, while the magnetic flux density, if there is no current, is continuous throughout the interface, the magnetic field is not, because H1, or rather H1 here, is B1 divided by mu, and H2 is B2 divided by mu. In one case, I wrote mu sub naught because it is in air. All right, so while B1 and B2 are continuous through the interface if there is no current, then H1 and H2 will be discontinuous by a large amount because mu sub r in magnetic materials is very high. And the tangential components, I mean the normal components, even if the normal components of B are continuous, regardless of whether there is a current or not, then the normal components of the magnetic field are discontinuous. So here, for example, we can write from the above that N, for each one case, N cross mu naught B1 minus N cross, H1, mu H2, are equal to mu j, depending on whether you are, and mu will be mu naught if you are just above the interface, is going to be mu just below the interface. All right, so this. And the other one gives us that n dot mu naught h1 is equal to n dot mu h2. All right. As a matter of fact, here, to avoid any misconceptions, I will have to write where this one is mu naught in air and mu in magnetic, depending on whether you are just above the interface or just below the interface. Okay, so I will also make it a little more clear. Above interface, just above interface. Above interface. And mu equals magnetic in magnetic material. Just therefore, just below interface. Okay. So these are the boundary conditions that we should pay attention to. And these are the ones that we used indirectly when we calculated the field inside the solenoid. All right. Practically, we calculated this condition. We used, I would say, indirectly, this condition. We use this condition because it does not matter if the current, well, not exactly, sorry. I apologize, this is the normal, but we used indirectly this condition. Yeah. All right. And we ignored, specifically we ignored the field outside. So I hope that that was not so confusing. I'm hoping that you are gonna read this carefully and you're gonna look at these boundary conditions. All right. All right, so again, what I would like to do is remind you that these boundary conditions, we are going to see them again in electromagnetics, but these are as they specifically apply to a field in magnetostatics where the current J is a DC current. All right, and again, what do they say? The first one says that if I have a current on the interface between air and magnetic material, then the tangential components of the magnetic flux density is discontinuous through the interface, which means as you just go through the interface, it jumps from one value to another, and that discontinuity is equal to mu j. all right? And the other one says that the normal component of the magnetic flux density through the interface is continuous no matter what, whether you have a current or not on the interface. And as I said, the one that we used for the solenoid is the first one. And this is the one that I would like you to remember, as well as the other one, all right? So we are going to see these two expressions side by side with the boundary conditions for electrostatics. When as I told you, I was going to prepare for Monday a table that shows all of the properties in electrostatics, all of the properties in magnetostatics. So you remember that we are looking at two dual fields. All right. So the next thing that we would like to do is, as I promised on Wednesday, we would like to see now what happens when we have not a infinite current wire, but a finite. Not that physically it exists. There is no finite section of a wire that carries a current that sits somewhere in space. The current is to flow on closed paths. However, we can consider a closed path that is made out of straight sections of line. All right, so in that case, it will be very useful to know how to calculate from its straight section of line the magnetic field that is coming from that part of the current, and then sum them all up, as you will see, when we have a square loop as opposed to having a circular loop. Okay, so what we are going to do next is to walk you through the solution of this problem. So now we have a section of a wire that carries a DC current, and the current flows from A to B, and you can see it here. All right, that's the direction of the current. And now we know, of course, first of all, that the magnetic field line is going to is going to close around the wire, all right? And if the current goes up, then the direction of the magnetic field is going to be this one. All right, now what we want to do is to take any point P here, take any point P, and we would like at that point to calculate the magnetic field. So how we do that? We take a section of a very short section of the current, like differentially short, like DL, and we write using Biot-Savart law, we write the magnetic field at point P. And according to Biot-Savart, this magnetic field is given by this equation. All right. Now, what do? We try in the cylindrical coordinate system. We have a cylindrical coordinate system, as you can see here. We try to express all of the vectors that we have in the Biot-Savart equation. We try to express it in the form of the vectors of the unit vectors of the cylindrical coordinate system. Okay, so first of all, DL. DL here is along the z-axis. Therefore, we write this vector DL as having a value dz, or a magnitude, and then a direction along the unit vector A sub z, or in fact, what I'm going to use here, since we have it in the notes, I will use here E sub z. All right. And then we write the vector r, which is the distance from dl to p here. We write it as a vector that is made out of two components, and we have seen this before. All right, so we just did exactly the same in the circular loop. So this vector has a value of rho along the radial direction, all right, and then has a component with z along the z direction. So this is E. All right. And then, since now we have found both dl, vector dl, and a vector r in the cylindrical coordinates, now we can write from there the magnitude of r as the square root of rho squared plus z squared. And then, of course, the magnitude of r to the third power is going to give us this expression. And now we go and substitute this back into Biot-Savart equation. And we rewrite this equation in this simplified form. All right. And then we can reduce these integrals. You can find them. We can find them in closed form. And we have this simplified expression, in which now I want to bring your attention to the values of these two angles. We call them here. You can either indicate them by A or by theta. Let's put theta here, because that's how we indicate it. Theta sub A. And remember, this is from the lower side of the section of the current is below that. From there to the angle between that section here and this distance of point A from point P, while this other one, theta B, is the angle that is made between the finite wire and the distance between point B and P. So it is very important to remember how we define those angles. And so I will put them here as such. So I'll put them here in red, so you remember that you have to check for the specific way we define them. All right, so now that we have this expression, all right, you can see it's a very simplified expression. Again, rho is the distance of point P from the finite section of the current or of the wire that carries the current, rho here. Theta sub A is this, and theta sub B is this one. All right, so now we are going to take those expressions and use them to find the magnetic field that is created by a rectangular loop that is defined on the XY plane. Okay. So the first thing we're going to do is to consider the rectangular loop as made out of 4 finite sections of current. So this is 1, 2, 3, and 4. Okay. And then we give the dimensions. And the side of this square that we have considered does not have to be a square. It could be anything, as a matter of fact. It's 4 centimeters, the current is 10 milliamps. And then we consider that the center of the loop is O. And we try, so in this particular problem, we want to find the magnetic field at the center of the loop. Very similar to what we did for the magnetic field at the center of the circular loop, all right? So, first of all, at the center of the loop, since this square loop is on the XY plane, that means, first of all, that the center of the loop is gonna be on the XY plane. So the Z component at point O is 0. All right, so it's right on the surface of the loop. Okay, so first of all, what we do is we try to use this formula here for this particular case. So O is at the center of the square. Therefore, all of the angles that you see here between the various sides, OA, OB, and AB, are 45 degrees. Okay. So now see how I was able, and I will correct, so we are here, I'll put theta. Theta B here, theta A. All right, so I'm trying to take AB and then put it in this form. Now, this AB that I have, that is not the same with the A and B here, all right? So as a matter of fact, I could, we don't get confused, I would call them here A prime, B prime, C prime, D prime. All right, so you have A prime and B prime here. All right, so A prime and B prime. So then now we use the formula to find the magnetic field from that side, A prime, B prime, at point O. Okay. And therefore, what we find, if we substitute for the two angles, one of the angles is theta A prime is 45 degrees, theta B prime is 135 degrees. All right, and that is important because if they were both 45, then the expression in the brackets would give you 0. So it will tell you that the magnetic field is 0, which is not possible. So theta B prime is 135, theta A prime is 45. Therefore, now that we know the values, we can substitute and we get this value for the magnetic field from that section of the rectangular loop. All right, we plug in the values and you get exactly this. Now, what we do is that we take all of the other sides of the square. We find the magnetic field to all of these sides, and then we sum them up at the center, all right? All of this is happening. And therefore, because this is a square, and because O, the point, the center of the loop, is at the same distance from every side of this square, that's point O, then we have that every section of the square gives the same magnetic field, and therefore the total magnetic field at the center is 4 times the magnetic field we found before. And therefore, now we can sum everything up and we find the total field at the center of the loop that is created. And from the magnetic field, we can go to the magnetic flux density. And now, again, as we assume, the same thing happens with the square loop with what we have seen for the circular loop. So the field, we can assume that for the same reasons that the field on the circular loop is almost everywhere the same with the value of its field at the center of the loop. And if this is the case, then practically we can identify the total magnetic flux density by multiplying the total, by multiplying, of course, the magnetic flux density from each section times 4, and then we can find the total flux through the surface of the loop by multiplying the total magnetic flux density with the area of the loop. All right. So then by doing these things, we can find the total flux. And then what is the next? Then the next from that would have been the next would have been to find the inductance of this loop, of the square loop, which is in fact nothing else but the total flux. And we can show the total flux like with psi or with phi. That was from another book that I was using. So if you show psi, you understand that is magnetic flux, but if you show phi, then you have to put phi sub m to remember, because we have phi both from electric and magnetic flux. All right, so we divide that by the current, and that is going to help us find the inductance. And the inductance here will be, of course, in henries if you use the appropriate units. And here the unit for the flux is amperes henries. So if we divide, how many do we say that how much the current was? It was 10 milliamps. So practically, this will be 10 to minus 10 divided by 10 to minus 3 amps, and here is going to be amps henries divided by amps, and therefore this is going to be 10 to minus 8 henries, which is 10 nanohenries. Okay, so that is the final example that I wanted to do for you. And then from there, we are going on Monday to solve these realistic inductors that we see in microelectronics. All right, and see how we are going to use this formula to find the inductance of something that is very realistic. Okay, so again, what we covered today was the boundary conditions. I will place that on the web together with the video. So the boundary conditions for an air magnetic interface, and also for an air dielectric interface, we said that the magnetic field does not see dielectric materials. So, and then we found the magnetic field from a section of current. And then we found from that the magnetic field from a rectangular loop. And that's what we covered today. All right, thank you very much. We'll see you on Monday. Goodbye.